Very good. Okay, well this is Math 265. It's been a while. I don't remember what date it is. It's November 12th? Okay, this is multivariable calculus. And last week, I guess it's been a week, we were looking at the cross product. So I'm going to just write down a slightly different way of computing the cross product.
Oh, you look so cute. I just rolled out of bed.
And after we do that, then we're going to do an application of it, show why we were doing this in the first place. And so we'll have to define the Jacobian of a transformation.
We did process, so. Yeah, we can.
Alright, so I just want to remind you that, well, we started off by defining the dot product of two vectors. And we did it because we wanted to know when it was the two vectors were orthogonal. And we showed that the dot product is 0 if and only if A and B are orthogonal. Right? That means they're perpendicular. And then the cross product was written down because we wanted to find out when two vectors, say, were parallel. Right? Or an alternative question that gave it to us was, if you have two vectors, like this, can you write down a vector which is orthogonal to both of them at the same time? So we had this A cross B. Now, A dot B was just a number, but A cross B is actually another vector. So this is a vector orthogonal to both A and B. And we saw there was really, well, there's a scalar that you can multiply by and get infinitely many of these things, but there's one that we call A cross B. And, well, there's two directions it could go. It can go up or down, but we use the right-hand rule to decide which. And then we also saw that A cross B equals 0 if and only if A and B are parallel. Now, unlike the dot product, which we can define for any number of variables, the cross product is restricted to vectors in R3. And the formula, remember, well, let's see, if we call, we should write A as like A1, A2, A3, and B is B1, B2, B3. And so the cross product should be a vector with three components to it. And remember, the way you can do it is, you write 1, 2, and 3, and you have to kind of go around this circle to remember the formula, and you have to start with 2. It's kind of a strange thing. So, you know, like A2B3 minus A3B2, comma, and you go to 3, and you get A3B1 minus A1B3, comma, then you go to 1, and you go 1, 2. So A1B2 minus A2B1. Does that look right? Okay, so this formula is not so hard to remember, actually. If you think about this circle and just remember you got to start at 2 and go clockwise around it. And then you always have to, once you pick these indices, and you just reverse them for the next bit. Okay. I want to show you another way to remember how to compute the cross product. No, I'm not going to claim that this is any easier than just memorizing this formula with, that circle in mind. But it's important. This method involves determinants of matrices, and that's important for some other things we want to do. So I'm going to show it to you anyway. So at some point you've probably seen matrices in your lives, yeah? High school sometime they showed it. So you have matrices of different sizes, but right now I just want to focus on square matrices. And let me start with just a 2 by 2 matrix. So 2 by 2 matrix, I don't need to write 2 by 2, I'm just doing it for your benefit. All right, is a square array of numbers, where here A, B, C, and D are all real numbers. And there's a lot of reasons why these matrices are important in mathematics. And I would love to go into those, but that's the subject of the course of linear algebra. So I'm not going to get to go in those today. But I will show you how to compute a certain invariant of the matrix called the determinant. So this is going to be a number that you can attach to a matrix. And sometimes you write det of that, or oftentimes the way they will write the determinant is just write the same matrix but replace the parentheses with giant absolute value bars. In any case, the formula is quite simple. You multiply along the diagonals and then you subtract. And the way when you go from left to right, that gives you positive stuff. When you go from right to left, that gives you negative stuff. So you go this way, you get AD. You go this way, you get BC. But because the BC is going right to left, you get a minus. So AD minus BC. Okay, so for example, the determinant of 3, 2, minus 1, 7 is 21 minus 2, which is 23. And this determinant is an important number attached to a matrix because, for instance, if the determinant is non-zero, that tells you the matrix has an inverse. That is, you can multiply by something and get the identity matrix. But we don't need any of that for right now. We simply need to know how to compute these determinants. And the thing that should make you suspect that this could be useful in writing down a formula for the cross product is, well, each of these is a product of two things minus a product of two other things. So actually, this is the determinant of, let's see, A2, B3 minus A3, B2. That's just this one little bit here. A2, B3 minus A3, B2. And we could do that for this one too. This is the determinant of, let's see, A3, B1 minus A1, B3. And this here would be the determinant of A1, B2, A2, B1. Okay. So this is already suggestive that there's something more you can do. Okay. We'd like to somehow, instead of having to compute, I mean, this seems actually much harder to remember than this, to me anyway. So we'd like to kind of put these all into one matrix. So we have A1s, A2s, and A3s, and B1s, B2s, B3s. You can't really fit those all into a 2 by 2 matrix. But we can fit them into a 3 by 3 matrix. So I need to tell you how to find the determinant of a 3 by 3 matrix. So let's say you have a 3 by 3, so it looks like A, B, C, D, E, F, G, H, I. Okay, so you've probably seen at some point how to do this expanding by minors or Kramer's rule. I've heard of these names before. Let me show you two ways to compute the determinant of a 3 by 3 matrix. The first way is the way I usually do it in my head, unless there's a lot of zeros lying around, which is the following. We're going to track diagonals, and the diagonals look like this. So there's a diagonal that goes A, E, I. Another diagonal looks like BF, but we need to always do three things. So if you do BF, it kind of overlaps over and hits the G. Okay, so the first one, A, E, I, then BF, G. And then the last one is C, DH. So let me use some different colors for this. Hopefully these work. So we're going to go AEI, BFG, and then CDH. Okay, so that's going to be our step one. And remember, everything that goes left or right gives positive. Just like with the 2 by 2 one. So we write down AEI plus BFG plus CDH. So this was C, that was H. Okay, so that's the first half. But when you do determinants, there's always a negative part. Okay, and that's where we're going to do the same thing but backwards. So we're going to do minus. Okay, now to do minus, we go along this diagonal. CEG. And then BDI. And then AFH. So minus CEG. Since all these are going right to left, they get minuses. Minus BDI. Look at your wee beady eyes. And then AFH. Okay. So you can compute it that way. Just you subtract, you add the left to right, you subtract the right to left. Okay. Now, what I'm going to do here next is not unique. There's a lot of different ways that I could do this. But let's say I focused on, say, this column here. Another way to compute this determinant is to say, okay, let me start with A, and I note that here I have AEI, and here I have minus AFH. So I could write A times EI minus FH. Okay, there's the AEI minus FH. Now, what is EI minus FH? Well, look here. EI FH. This is just the determinant of that little 2 by 2 submatrix. Okay? This is A times the determinant of that matrix. Okay, now I can move, say I move down this column and I go to the D. I say here, now let's see, I have a D times CH, and then minus BI. Well, now let's see, where can I get a CH minus BI? Well, let's see, if I have a D here, let's see, where's the CH and the BI? Well, here I have a BI and here I have the CH. Now the determinant would be BI minus CH. All right, if you just forgot about this row here, bi minus ch, it's going the wrong way. So what I could do is instead write this as minus bi minus ch. Okay? I've just reversed the order here. And now this is, so minus d times the determinant of bchi. Okay. Now I go down to the g. So remember I've hit this one and that one, I've hit this one and that one. And now this g shows up in the last two. So what do I get? I get g, I have a bf, and then I have a minus ce. Well, let's take a look. Look, bf and ce, it's just the determinant of that little 2 by 2 matrix. So plus g times the determinant of b, c, e, f. Okay, so let's take a look at what you do. You pick a row, and this would actually work if I chose any row or any column. So I pick a column, actually, is what I did. And you start with your A, and then you cross out whatever, you just cross out this column and this row, and that leaves you with a 2 by 2 matrix. Cross this out, you get EF, HI. That's exactly what you compute the determinant of. Then you do the same thing for D. Cross out its column, cross out its row. You get BI and then the CH. Okay? But it gets a minus sign. And then you do the same thing with G. You cross out the column, you cross out the row, and you're left with BCEF. You compute its determinant. And if you want to know what sign should go in front, there's a way to map it. On every spot you can put a little sign, and it just alternates. So it starts with plus, and then it just alternates going across. So that tells you what sign you have to put. Okay, so we'll do a quick example. So let's compute the determinant of 3, 0, minus 1, 2, 5, 1, 0, 0, 4. Okay. So first, let's use the crisscross method. If you do that, you go across the diagonal first, so 3 times 5 times 4, so that's 15 times 4 is 60, plus 0 times 1 times 0, which is 0, plus minus 1 times 2 times 0, which is still 0. Then you have to go backwards. Minus 1 times 5 times 0, nothing. Minus 0 times 2 times 4, nothing. Minus 3 times 1 times 0. Oh, nothing. Cool. So determinant 60. On the other hand, if we used this method here, right, you should choose. You can choose any row, choose any column. Which one's going to be the best to choose? Well, remember what you're going to have to do. You're going to have to crisscross, right? And if you pick, say, this column, you're going to have to start at the 0 and cross these out and look at that 2 by 2 determinant. And then multiply by 0. But that's going to be nice. You multiply by 0, it'll be done. Then you take this 5, you crisscross, and you take 3, 4, 1, minus 1, 0, and then multiply by 5. And then the last one, you'll cross like this, and you'll compute the determinant, 3, 1, minus 1, 2, and multiply by 0. Again, multiply by 0, you don't have to do anything. So what's the best sort of row or column to choose? It's one with lots of zeros, because in the end, all you do is multiply by 0, and so you don't have to compute the determinant. So there are two good choices here. You could either choose this middle column, because that has 2 zeros, or this bottom row. All right? So let's choose this bottom row. If you choose the bottom row, then you don't have to compute the first two, only the last one. And when you do that, you cross out this row and column, and you just have to compute the determinant of this little matrix, which is 15 minus 0, which is 15, multiplied by 4. 15 times 4 is 60. Okay, cool. It works. Okay. So you have a couple of options how you go about doing it. Okay, so how do we work this in with the cross product? Well, it turns out that if I write this in a slightly different way, it's a little easier to see. So A2B3 minus A3B2, comma, what is it, A1 next? No, A3 next, of course. All right, these should always match. A3B1 minus A1B3, comma, A1B2 minus A2B1. I could write this in terms of I, J, and K. Okay, remember I, J, and K are these vectors, the standard unit vectors. So I could write this as A2B3 minus A3B2 I plus A3B1 minus A1B3 J plus A1B2 minus A2B1 K. Okay, so remember I is the one that goes in the x direction, it's a unit vector, J goes in the y direction, K goes in the z direction. And now look here, this actually looks a lot like sort of what we're getting at here. You have some coefficient which is a determinant, and then you have something outside that you multiply by. So let's see if we can't make this look right. So let's say, well, if I'm going to do this game where these are supposed to be the things I multiply, I can put the I, J, and K in some row or some column. Just for ease, let me put them on the top row. Okay, so I'm going to expand on this row. So it should be I times, well, let's see, you'd kill that row and column, so it should be the determinant of this matrix. So that means that it actually should be A2, B3, minus A3, B2. So it's I times the determinant of this little 2 by 2 matrix. Okay. Then I need to do J times the determinants. Right, well, let's see, it should be A3B1 minus A1B3. Ah, but remember, that position is going to get a minus sign. So I can swap things around as I need to. So let's see. It's going to kill that and kill that, so it should be A1B3, good, minus A3B1. The determinant here would be A1B3 minus A3B1, which is the opposite of this, but that takes into account that minus sign. Okay, and now let's see, does it make sense with the K? Well, the K gets a plus sign, and then you kill those, and you take this determinant, it's A1B2, good, minus A2B1. Perfect. So the cross product is actually just the determinant of this 3 by 3 matrix. So this is another way to remember. And look, this, what is this? This is just IJK. This is just A. A1, A2, A3. And this is just B. B1, B2, B3. So it's a nice condensed way to write everything down. Okay, questions? Has anybody not seen these before, these determinants? Okay. I think it's pretty standard fare in some class in high school nowadays, so I'm not surprised. Okay. So let me just do, what's that? Let's just do a quick example. 1, 2, 5, and 3, 0, minus 2. Okay. So if you want to compute the cross product of these two vectors, you could use this formula to compute it, or you could set up the determinant. Let me switch from this determinant of blah notation to just the absolute value notation. It's a little faster. Okay, and I just put A in the middle row and B on the last row. Okay, and now I want to compute the determinant. So you have some choices how you want to compute it. You could use the crisscross method, or you could expand on one of the rows or columns. Any preference at this point? No? Okay. How about, well, there's a nice 0. So do you want to expand on maybe this row? Because that'll kill, that, then you don't have to make any choices. Okay, so let's see. So here you have a 3. So you kill that row and column, and so you just compute the determinant here. And that gives you 5j minus 2k. Okay, and then you have to multiply by 3, because that's the coefficient. Okay, and then over here, you have a minus 2. So minus 2 times, let's see, 2I minus j. And so if we compute this, let's see, how many i's do you get? Well, there's no i's up here, so you get minus 4i. And then j's. Here you have plus 2j and 15j. So that's 17j. And then you have minus 6k's. Okay, so there's your cross product. And of course, if you wanted, you could write this as minus 4, 17, minus 6, as you like. Anyways, I'm erasing here. I did put a new homework up in case you didn't see it. Lots of fun with cross products, but start early because there's a lot of work on it this time. So start early. All right, let's do one more example here. So let's find.
I have a question. Can you find the determinant of any kind of matrix?
You mean any size matrix?
Yeah.
No, only any square matrix.
Okay.
But I haven't told you actually how to do that. Oh, well, I mean, you can actually use this expanding along a row and column, or around a row or column to do any matrix. But you have to kind of do that inductively then, because if you do a 4x4, now you have to compute 3x3 matrices, and then, yeah, it becomes more cumbersome. That's why we have computers. So let's find the area of a triangle with vertices 1, 4, 6, negative 2, 5, 1, and 1, negative 1, 1. And just for ease of reference, let me call this point A, that point B, and that point C. So, well, this triangle sits in some plane, and let's just assume we've tilted our head so that that plane is the whiteboard, and that we don't care about directions or anything, that we just say that, relatively speaking, we've somehow put these in the right direction. So we'll put A there, we'll put B there, we'll put C there. And there are, of course, vectors that go from A to B and vectors that go from A to C. And, of course, you could complete this diagram if you liked. And you get a triangle, and it has a certain area. And the question is, what is the area? Seems like you should be able to answer this pretty easily. You've all taken, 4th grade geometry. Area of a triangle. 1/2 base times the height, right? course, where do you get that 1/2 from in the area of a triangle? Why is it 1/2 the base times the height?
Because it's half of a rectangle.
It's almost half of a rectangle. Of course, that would only work if you have a right triangle. Yeah. In fact, a rectangle is just a very special case of a parallelogram. So the area of a triangle is half of the area of the parallelogram you get when you double the triangle. Right? And the area of a parallelogram is the base times the height. Okay, that's one way to put it. But we actually saw how to compute the area of a parallelogram where you were given these two vectors. Had to do with a certain product. Remember, we finished last time, we talked about the volume of a parallelepiped, right? But that was the harder case. The first thing we said, oh, what about the area of a parallelogram? So the area...
The scalar triple product. Oh, that's the...
Scalar triple product, that had to do with the volume, right? Before that, right at the beginning. Let me give a name to these vectors that go from A to B and from A to C. So the area of the parallelogram is, what is it? It's the magnitude of
C times the height.
It's the magnitude of the cross product of those two vectors, B and C. So if you took that cross product, it actually, the magnitude of it was the area of that parallelogram. So the area of the triangle ABC is a half of that. I can see you guys were diligently studying your notes over the last week. Okay. So all we need to know is what are these vectors B and C, and then we can compute the cross product. So, well, let's see. B is a vector going from A to B. Well, what is that vector? You actually just get it by subtracting B minus A. Right? If you take these points and you subtract them, that will give you the coordinates. Right? Subtracting this, doing this minus that, that's like bringing it back to the origin somehow. So B is given as -2 minus 1, comma 5 minus 4, comma 1 minus 6. And C is 1 minus 1, comma minus 1 minus 4, comma 1 minus 6. So B is -3, comma 1, comma minus 5. And C is 0, comma minus 5, comma minus 5. You think about it, when I do B minus A, I mean the coordinates of those points, I'm just saying what's the distance between the x coordinates, what's the distance between the y coordinates, what's the distance between the z coordinates. So it's just telling you the length, it's just giving you the coordinates of the vector that's going between them. And so a half, let's see, of the norm of the cross product, well, let's see, that's a half of the norm of, well, I got to do B cross C. So what is B cross C? Well, it's the determinant of the matrix that has ijk, and then B is -3, 1, minus 5, and then C is 0, minus 5, minus 5. So you should be careful here because the absolute values on the outside, that's the norm. The absolute values on the inside, that's the determinant. Okay, so let's see. Well, we have a 0, so that suggests a good idea is to expand along either this column or this row. Let me use, say, this row because the numbers are smaller. So let's see. So we start with I. So we get I times, okay, we need to do the determinant of this matrix. So minus 5 minus 25. So minus 5 minus 25 is minus 30. Okay, and then here we have a minus 3, but remember, when we write down that matting, that minus 3 gets a minus, so it becomes actually a plus 3 times, now we need to do this j minus 5, k minus 5, so minus 5j minus 5k, so plus 5k. And then this 0, you don't have to do anything with. So now, let's see, this is minus 30i minus 15j plus 15k. And so now you just need to compute the norm of this, which is easy. You just do 30 squared plus 15 squared plus 15 squared square rooted multiplied by a half. So that's 900 plus 225 plus 225 to 900 plus 450, which is 1350 square rooted over 2. So a half square root of 1350. I'll let you simplify the square root of 1350 a little bit. Okay. So that's how we can do it. Uh-oh. I got a different number. Let's see. Oh, I ended up with a 75J. Oh, did I make a mistake here? Let's see. This was 5J times 5 is 15. Oh, here. Okay. So either there's a mistake on the board or a mistake in my notes. Bonus points if you can resolve that.
Which column or row did you pick?
What's that?
Which column or row did you pick?
So I was using that column. So when I did this one here, should have gotten minus 5j and then plus 5k times minus 3 times minus 1. So maybe it's just a mistake in my notes. It could be. Okay. John?
There's a mistake on the first one on the I.
This? You mean?
It's supposed to be 20.
20. So it should have been minus 1 times minus 5 is 5.
Yeah.
Minus 25. So minus 20. Wait a second.
Minus 20.
No. Oh, yeah, okay, wait. So
there's no negative sign in front of the 1.
oh, that's from my dots.
Yeah.
Okay. Minus 5. Then this gives you plus 25, but you have to subtract it, so it's minus 25. So I think this is minus 30. Because this is minus 5, this is 25, but you have to subtract the 25, right? Because you're going right to left. Okay.
No.
Okay. So up to arithmetic errors. This is the correct answer. Or as I like to say, it's correct up to a constant. Okay. All right, so I haven't really told you why it is that we wanted to talk about these cross products. I mean, it is kind of nice that you can use them to find areas of parallelograms and triangles and parallel hypens and so forth. But the real reason I wanted to tell you about them is because we did this whole unit on double and triple integrals and then changing them into polar coordinates and spherical coordinates. And every time we had to change coordinates, we had to figure out what should happen to the integral. For instance, when you changed to polar coordinates, it wasn't for free. You had to pick up something. Remember what you picked up?
An R.
An R. And when you changed to spherical coordinates, you picked up something. A rho squared sine phi or sine phi, depending on what you like. Okay. So every time you change coordinates, you're going to pick up something. And the question is, what are you going to pick up? And there is a general procedure for figuring this out without having to go back and drawing, some region and defining, in my new coordinate system, this is what I mean by a rectangle, and now I'm going to subdivide it into regions, and I'm going to take points and evaluate the function of those points and take the limit of blah, 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 right? We'd have to do that every single time, and this could be very, very bad. So we don't want to have to do that. So let me show you kind of a stupid example that you already know to sort of tell you where we're going with this. So at this point in your mathematical lives, when you see this integral, you know what to do. What am I going to do?
U substitution.
Of course, U substitution, right? I see that x squared up there and I freak and then I go, oh wait, there's an x down there. It'll be nice, I'll cancel out. So you might say u equals x squared and then du equals 2x dx, and you say, that 2 is going to have to be replaced with a little 1/2 out front, and then I can change my limits of integration, and so forth. Okay. It's a change of variables. If you think about it, that's exactly what polar coordinates and spherical coordinates were. It was a change of variables. You just changed your x's into thetas or r's or whatever. Now, I want to write this in a slightly different way. Instead of writing u equals x squared, I'm going to solve this for x. So writing this is the same thing as writing x equals the square root of u. This makes sense because, well, between 0 and 2, both the u and the x are always positive, right? So there's no ambiguity there. And then, well, I could write dx as being, remember u, of course, is u to the, square root of u is u to the 1/2. This is 1/2 u to the minus 1/2 du. Or if you like, dx du equals 1/2 u to the minus 1/2. Okay. We've actually seen a couple of places in 166 where it was useful to, instead of writing u equals, it would write x equals. But I don't really care about that. It's just a different way to write it. And so now our integral, right, well, this is x equals 0 and x equals 2. We could rewrite this as, well, let's see, if x is 0, then what's the u supposed to be? Well, u is going to be 0 also. And if x is 2, then the u is going to end up being 4. But now we can rewrite this in terms of the u's. You know? I could write square root of u, e to the u, and then, well, what I'm going to do, I still got this dx lying around that I can't really substitute away for, but I can write it like this. Dx du times du. And you'll see those will cancel, and there's our dx back, or this dx. Okay, so I could write it like this. So everything now is a function of u. So I have here, well, this is some f of u, and this is, well, this is a dx du, and this is a du, and everything's functions of u. Okay, so this is quite nice. And somehow, right there, that's what you're adding on. That's the important thing that you're adding. And it's sort of corresponding to that r that we do get when we switch to polar coordinates and to the rho squared sine phi when we switch to spherical coordinates. that's what we're aiming at. So we're going to do something that's maybe a little abstract right now, but bear with me for a second. Okay, so why is it that we do these sort of transformations? Well, for this one, I mean, it was clear, this function was really hard to integrate as it was, but when you do a substitution, then it became very easy to integrate. When we switched from rectangular coordinates to polar coordinates, it was the same thing. We could take regions that were really nasty to integrate over, at least they didn't look very nice anyway, and then we could turn them into polar rectangles. It became very easy to write down what the limits of integration were. And the functions would get easier. Right? If you had x squared plus y squared, they would just turn into r squared. Okay? So that was the whole point. So the way this is going to work is going to look a little bit backwards. We're going to start with some sort of nasty region that we're not terribly happy with. Maybe. Okay, but when I say start, I actually mean end. And then over here, we're going to have a nice region that we like. Good, solid rectangle. Yeah, everybody's happy about those. So let me give a name to this point down here. Let me call this U naught, V naught. And this will be the U axis, and this will be the V axis. And over here, this will be what we actually want to end up with. There's the x axis, and there's the y axis. And let's call this delta V and this delta U. So that's the amount of change as you go across this line here. Delta V, that's how much you go up. So this is something that's really nice. This is something that we have that's really garbage. And you try to define a map, which we'll call T, that takes this region and sends it over into this region. If you do that, then this point down here, that would correspond hopefully to your T of U naught V naught. So this point heads over here. And this line here, that should map over there. And so that's kind of 1. And then this 2, right, this bit, that should map over to here. Okay, and so forth. This line should map over there, and this line should map over there. So you do it in some nice, continuous way, right, that preserves everything. So if we do that, then this t should be, well, this is going to be kind of strange. It's a function, but it's actually going to be a function that's composed of a couple of different functions. So the x-coordinate is going to be given by a function g of u and v. And the y-coordinate is going to be given by, say, a function h of u and v. And you should think back to when we did like the chain rule 2f2. Where you had two functions and they're both given as functions of u and v. So this region is given in terms of x and y, but then x and y individually are functions of u and v. So you get these two things. So we're going to write down what's going to be called the Jacobian of this t. And this t is called a transformation. That's why we call it t. Okay, we're going to transform this region into this one. And the Jacobian of t is, well, we're going to write j of t for the Jacobian. And it's going to be the determinant of a matrix. And the matrix is simply, you take the partial derivative of G with respect to U, then the partial derivative of G with respect to V, the partial derivative of H with respect to U, and the partial derivative of H with respect to V. And of course you could work this out fairly quickly. This is GU HV minus GV HU. So this is called the Jacobian T. So let me give a name to this region on the right here, R for right. We'll call it R. The reason why this Jacobian is interesting is because the Jacobian can be used to find an approximation for the area of R. So the area of R is approximately equal to well, it's going to be the absolute value of the Jacobian evaluated at U naught V naught. Okay, so the Jacobian, all right, it's just a product of these partial derivatives. So it's not a number, it's a function usually. But you can evaluate it at the point U naught V naught. So you evaluate the point U naught V naught, and then you get a number, and you take the absolute value of that number, because this is going to be area. And then you multiply by delta U and delta V. So for small rectangles, over here, this becomes a better approximation. So delta U, delta V is, of course, the area of this rectangle. But when you apply T, the rectangle gets transformed, because T is a transformation. And when you do that, the area changes. And how much does it change by? Well, it turns out to change by, well, not exactly, but almost the absolute value of the Jacobian at the point U naught V naught. Of course, the bigger this gets, the farther away points in here away from U naught V naught, the worse the approximation is. But the closer, the smaller it gets, the closer all the points are to U naught V naught, and the better this approximation gets. Okay, fine. Now we have to write down something long. Okay, so in the end, you're starting with something nasty that you don't like. You're trying to integrate, say, a function over R. Okay, and let's see, let me give a name to this area. This is a, say, delta A. Then this double integral should be approximately, well, we've seen what this is before. You have to do this double sum. Say from I equals 1 to m, and j equals 1 to n, and then you do f xi yj delta a. Yeah.
What's the extra bar represent?
This is just saying a value. Oh, not this one or this one?
Yeah.
This is not the absolute value of the bar. I know it's a little confusing. Those two are the absolute value bars. This one here says restrict to U naught V naught. Let me make it a little smaller. It's a little confusing, the notation. Okay, so the double integral is approximately equal to this double sum, right? You have to take the limit to get equality. Okay, but now this is approximately equal to, well, again, we have this double sum. Delta A, I can transform into this bit, because that's what delta A is approximately equal to. And the f of xi, f of yj, well, I use this transformation, this t here. So I write this as f of g of ui vj, comma h of ui vj. And then I multiply by the absolute value of j of t evaluated at u naught v naught times delta u delta v. Now if I take the limit as m and n are going to infinity, then I get the double integral. And so that tells me that the double integral over r, f of xy dA, equals the double integral over S, so let me call this region over here S. This is just this nice rectangle. F of g of uv, comma h of uv. Right, so I do the change of variables. But then I need to put this j of t in. So it becomes the Jacobian times, it becomes du dv. So this Jacobian, that's the extra garbage that you're going to pick up every time. Oh, I forgot. Absolute values. In the limit, of course, you don't need to evaluate this point u naught v naught, because that's changing. Okay. There are some restrictions. You cannot do that for any t that you could possibly write down. So let me write some of these things up. So this is the change of variables formula, and the above formula holds for t satisfying the following laundry list of properties. You are limited, in a sense, to what t's you can use. So first, well, this t is made up of two functions, g and h. And those g and h should be particularly nice functions, namely they should have continuous partial derivatives. And we've seen that condition before a lot. And it's a useful one. So g and h have continuous partial derivatives. Second, the Jacobian should not be the zero function. Imagine if it was, what would happen to our integral? If that was zero. Yeah, this would be quite bad. Well, t, of course, should go from some region S onto your R. Let's see. F needs to be continuous on R. That's so that, well, it's not that it needs to be, but it'll be helpful because it'll mean that this double integral exists. Remember, if the function is continuous, then the double integral exists. And then this is a this is one you have to think about a little more. So R and S should be type X or type Y regions. And the last thing is that this t should be a one-to-one function. That means it's not going to take two different points and send them to the same point. Except possibly on the boundary. Okay, so it's possible that things on the boundary could get sent to the same point, but all this stuff in the middle can't get sent to the same point. Okay, so all the problems that I give you, these things are going to hold, but you should know, of course, the conditions are there, because as you saw in the midterm, I do like to give problems that at least relate to those conditions once in a while, but at least when you solve the problems, it's okay. We have a couple minutes. I just want to quickly show you how this works for polar coordinates. It's very short. Actually, oh wait, I forgot. That clock is really misleading, isn't it?
Yeah.
No. Yeah, okay, so we have like 10 minutes. That's good. Okay. So, let's look at how we could have simplified things now for polar coordinates. So for polar coordinates, we know that x gets transformed by r cosine theta, and y is transformed by r sine of theta. So that's how I build my t, right? My t is r cosine theta, comma r sine theta. Okay, so this is my g of r theta, and this is my h of r theta. So what's the Jacobian? Well, the Jacobian is, I need to take the determinant of, well, let's see, the partial of g with respect to r. That's the first bit. So I need the partial of r cosine theta with respect to r. Partial derivative of this with respect to r, well, that's just cosine theta. Okay, just using this formula down here. And now I need the partial derivative with respect to theta of g. So what will that be? Derivative of cosine of theta is minus sine of theta, so it becomes minus r sine of theta. And then I do with h, so I do the derivative with respect to r, that will just be sine theta. And then the derivative with respect to theta will be r cosine theta. And this is equal to, let's see, r cosine squared theta. Minus minus is plus r sine squared theta. Oh, that's nice, isn't it? What does this equal? R. Just r. Of course, r we can assume is positive, so we don't need to take the absolute value. No, that r, remember I said the Jacobian is the thing that you add? In polar coordinates, what's the thing that we add? We add an r. That's our r. That's where it's coming from. So that tells us that if you integrate just your standard function, f of x, y over some region r chosen appropriately, this is the double integral over, well, we changed it into an s, whatever that s is supposed to be. F of r cosine theta, r sine theta, times the Jacobian, which is r dr d theta. So there you have our polar coordinate transformation.
I have one question I was trying to do.
There's the function, there's your j of t. Okay. I'm hesitant to start the next example. I don't want, the problem is, the tricky part in all this is coming up with the right s. This is kind of the hardest part, and we don't have enough time to really go into that in this next one, so I'm just going to stop right there. And we'll pick up next week. We'll do some examples. And, all right. And then we'll also see, so I should mention, this Jacobian is for transformations dealing with functions of two variables. But there is nothing that stops you from doing this with more than two variables. So we're going to be able to write down the Jacobian for a transformation with three variables, and then we'll see that the Jacobian of the transformation that takes you to the spherical coordinates is exactly rho squared sine of phi. So it'll all come out naturally. Okay. And one of the things that you should be thinking about with this t is that it's actually a function of two variables. That is, it's a function that eats two variables, u and v, and spits out not just one number. It actually spits out two things. I mean, even if you tell what u and v are, you're getting something comma something. T is a function from R2 actually to R2. So the value you think about is a vector. And that's going to be the next thing that we go into, are functions whose values are vectors. And we're going to pick things up quite a bit, actually. The speed of the course is going to go up now.